Good day. This video discusses metallic transmission line equivalent circuits. Characteristics of a transmission line. The characteristics of a transmission line are determined by two things. First, we have the electrical properties. This consists of the wire conductivity of the transmission line itself and the insulator dielectric constant. Second, we have the physical properties. These are the wire diameter and the conductor spacing. Line constants. There are two kinds of line constants. First, we have the primary electrical constants of a transmission line. These are the distributed parameters: resistance, inductance, capacitance, and conductance. The primary line constants are parameters that describe the characteristics of conductive transmission lines. And then we have the secondary electrical constants of transmission line. These are the characteristic impedance and propagation constant. The secondary line constants can be used, for instance, to compare the characteristics of a waveguide to a copper line, whereas the primary constants have no meaning for a waveguide. Now, how do we analyze the primary electrical constants? To analyze the primary electrical constants, we have to take a portion of the transmission line, not the entire transmission line, but only a portion of it. Like the figure below, as you can see, there we have a transmitter and an antenna. Transmitter is our input end and that antenna is the output end. The two are connected by a transmission line, and to analyze the transmission line, we have to take a portion of it, and then we can now find the lumped parameters. Now, a lumped circuit model is a part of a large circuit where the parameters are concentrated at one place. This is the portion of the transmission line that we have taken to analyze. And the resistance, capacitance, inductance, and conductance are called the lumped parameters. These lumped parameters can be connected to form the distributed circuit model. Now, as you can see, the distributed circuit model is just a collection of lumped circuit model. In here, we have the inductance, resistance, conductance, and capacitance. These are uniformly distributed throughout the length of the line, and therefore, these are commonly called the distributed parameters. For primary electrical constants, we have R. This is the series DC resistance. It has the unit of ohm per unit length. It is the opposition to current flow. And then we have L, our series inductance. It has the unit Henry per unit length. And this is the self-inductance of the current carrying conductor. Next, we have our capacitance. This is our shunt capacitance. It has the unit of farad per unit length. This is due to the two conductors separated by an insulator. This is actually the principle of a capacitor. Two conductors separated by a dielectric material, which is an insulator. And lastly, we have our conductance. For a transmission line, this is our shunt conductance. It has the unit of Siemens per unit length. It is the leakage current due to the imperfection of the insulating material. Now, as you can see, we'll analyze two types of transmission line in the slide. On the left side, we have a two-wire transmission line, and on the right side, we have a coaxial line, commonly called a coaxial cable. For the two-wire line, it is just two wires. As you can see, this is the cross-section. So the two wires are going out of the screen, so you can actually see only two circles. Now, the two wires are separated by a distance of capital D, and then the radius of the wire is also given. It is small r. The two lines have the same radius, so we only have 1 r to represent both their radii. And then for the coaxial line, we have our current carrying conductor in the center. So it has a diameter small d. And then on the outer side, we have the grounding wire. This is capital D. This is also a conductor that grounds the signal or serves as the ground of the signal. So to solve for the series inductance in Henry per meter, we have two different formulas, one for two-wire and one for coaxial. For two-wire, we can solve the series inductance by this formula. Inductance is equivalent to mu, this is the permeability, divided by pi times the natural logarithm of the distance between the two wires divided by their radii. And for coaxial cable, we have the inductance is equivalent to the permeability divided by 2 pi times the natural logarithm of the diameter of the outer cable divided by the diameter of the inner cable. And then for the series capacitance, that will solve with the unit of farad per meter. We have the formula for two-wire capacitance is equivalent to pi times permittivity divided by the natural logarithm of the distance between the two wires divided by their radius. And then for coaxial, we have capacitance is equal to 2 pi times the permittivity divided by the natural logarithm of the outer diameter divided by the inner diameter. For the secondary electrical constants, first let's take a look at the characteristic impedance. This is also known as the surge impedance, and it is represented by the symbol Z sub O. The characteristic impedance is the ratio of voltage to current at every point along the line. You may remember previously that if we are sending a sinusoidal voltage across the line, the current would also be a sinusoid. If a load equal to the characteristic impedance is placed at the output end of any length of line, the impedance will appear at the input terminals of the line. This is known as a matched line. And finally, the characteristic impedance is the impedance seen looking into an infinitely long transmission line, or the impedance seen looking into a finite length of line that is terminated in a purely resistive load equal to the characteristic impedance of the line. Now let's take a look at different formulas to solve for the characteristic impedance of a transmission line. We have more than one formula since the characteristic impedance calculation will depend upon the kind of the transmission line that we are looking at. Let's take a look at the representation of a characteristic impedance. In the image, we have our source. This is where our voltage comes from, or where our power comes from. Then we have our load. As you can see, our load impedance, Z sub L, is equal to our characteristic impedance, Z sub O. So this is a matched line. And then in a transmission line, we have the so-called lumped parameters. So we have the resistance, inductance, conductance, and capacitance. In here, the inductance and capacitance are represented by their impedance equivalents. So we have J omega L for inductance and J omega C for capacitance. And this particular transmission line is only one unit length or one section in length. So to solve for the characteristic impedance in this particular example, we have the formula Z sub O squared, this is the characteristic impedance, is equal to Z1 times Z2 plus the load impedance squared divided by N, wherein N is the number of sections. Now, Z1 and Z2, as you can see from our example, is equivalent to the lumped parameters. Z1 is equal to our resistance R plus J omega L, and Z2 is equivalent to our conductance, and capacitance. So for Z2, we have 1 over j omega c plus g. Now, Z1 times Z2 is only applicable for one section. And if we have multiple sections, we have Z sub L squared divided by N. Okay, remember this formula. Next, for infinite number of sections, we cannot simply put infinity as the value of N. So we have the formula Z sub O is equal to the square root of Z sub 1 times Z sub 2. Or in simpler terms, we have the square root of resistance plus j omega L divided by R conductance plus j omega C. Now, as you can see, omega is equivalent to R 2 pi times frequency. So the characteristic impedance is also dependent on frequency. There are special cases for which we can simplify the calculation of characteristic impedance. First case, it's for extremely low frequencies, the resistances will dominate. That is, when resistance R is a lot greater than j omega L and the conductance G is a lot greater than j omega C. Because imagine, at low frequencies, since omega is equal to 2 pi f, we will have 2 times pi times a very low frequency times this conductance. It will leave a lower value than, say, the resistance R, and the same goes for the capacitance and conductance. So the approximation would be the characteristic impedance Z sub O is equal to the square root of the resistance R divided by the conductance G. The second special case, it's the opposite of the first. It's for extremely high frequencies. The inductance and capacitance will dominate. So this happens when j omega L is a lot greater than R and j omega C is a lot greater than G. So just the opposite of the first one, you can imagine the calculations for this. Since j omega L and omega is equal to 2 pi f, f will have a very high value. So j omega L will have a very high value as well as compared to R. And the same goes with j omega C and G. So the formula for this would be the characteristic impedance Z sub O is equal to the square root of j omega L divided by j omega C. The j omega would cancel out, which leaves square root of L over C. Okay, now the first transmission line is a two-wire parallel line, or what we call a balanced transmission line. The formula for the characteristic impedance for this line is Z sub O is equal to 276 divided by the square root of epsilon R times the logarithm of capital D over R. Wherein, if you can remember from the previous slides, the capital D is the distance between the conductors, R is the radius of the conductor, both conductors are assumed to have the same radius, and epsilon sub R is the dielectric constant. This is the relative permittivity of the insulating material. Different insulating materials would yield a different dielectric constant. Usually this is given in the problem. Now another formula for characteristic impedance. This time it's for a coaxial cable. The formula is Z sub O is equal to 138 divided by the square root of epsilon R times the logarithm of capital D over small d. Wherein, if you can remember, capital D is the inside diameter of the outer cable, and the small d is the outside diameter of the inner cable. And epsilon sub R is a dielectric constant of the insulating material. So it is quite easy to understand. The capital D is for the outer conductor, which is much bigger than the inner conductor. So small d is the diameter of the inner conductor. The next transmission line, we have a strip line. A strip line consists of a printed conductor between two ground planes typically formed from copper-clad polyethylene sheets. So let's take a look at the formula. So the formula for this, we have the characteristic impedance Z sub O is equal to 60 divided by epsilon R times the natural logarithm of 4 times D divided by 0.67 times pi times the width W times the quantity of 0.8 plus T over H. Now as for these variables, Z sub O, of course, it's the characteristic impedance. Epsilon R, the same as before, it's a dielectric constant. In this slide, there are a few of the most commonly used dielectric for the strip line. First, we have FR4. FR stands for flame retardant. So FR4 is a glass reinforced epoxy laminated material. So we have FR4 fiberglass. Epsilon in this case is equal to 4.5, and for Teflon, epsilon is equal to 3. Now, W is the width of the conducting copper trace. The copper trace is in between the ground planes. So as you can see in the diagram, W is the width of that copper trace. And T is the thickness of the same copper trace. D is the thickness of the dielectric material. And lastly, H is the distance between the copper trace and the ground plane. Usually, the copper trace is placed such that it will have an equal distance between the two ground planes. So H can be taken from any of the ground plane to the copper trace. Next, we have a microstrip. A microstrip is a miniaturized version of a strip line best suited to circuit integration of semiconductors. So the formula for the characteristic impedance of a microstrip is this. Z sub O is equal to 87 divided by the square root of epsilon sub R plus 1.41 times the natural logarithm of 5.98 times H divided by 0.8 W plus T. Now for the variables, W is the width of the copper trace, so same as the strip line. T is still the thickness of the copper trace. H, the same, the thickness of the dielectric, and epsilon sub R is just the dielectric constant. So same as before, these are the commonly used materials. We have FR-4 fiberglass and Teflon. So what's the difference between a microstrip and the strip line? First, the construction. As you can see, the conductor is now above the dielectric substrate and there is only one ground plane which is located beneath the dielectric substrate. So this is best used for ICs and for PCB layouts. Next, we can solve for the inductance and capacitance of a microstrip. First, the inductance L is equal to mu, or the permeability, times the height of the dielectric substrate divided by the width of the strip conductor. Now for capacitance, C is equal to epsilon, or the permittivity, times W divided by H. So ZO can be simplified. When height over width is a lot less than 1, we can actually solve for ZO this way. The characteristic impedance ZO is equal to 120 pi times H over W. And then lastly, we have multi-track microstrip. So for a multi-track microstrip, as you can see, there are multiple copper traces. This is the difference of a multi-track microstrip from a regular microstrip. So the formula for a multi-track microstrip is Z sub O is equal to 276 divided by the square root of epsilon r times the logarithm of pi times x divided by w plus t. Now these are the variables that you have seen from the microstrip and the strip line, but it has an added variable, the small x. Now this small x is the distance between the two copper traces. Important notes. First, electromagnetic waves travel down the line without reflections. Such a line is called a non-resonant line or a non-resonant circuit. 2. Line losses on a non-resonant line are minimum per unit length. 3. The incident voltage and current at any point along the line are in phase. So this is what we want, a non-resonant line. 4. Any transmission line that is terminated in a purely resistive load equal to Z sub O acts as if it were an infinite line. So this entails that there will be no reflection that will come from the load. So this happens when Z sub I is equal to Z sub O. There are no reflected waves and voltage and current are in phase. So there is maximum transfer of power from source to load. Again, this is what we aim for in transmission lines. The next secondary constant, the propagation constant. Propagation constant, denoted by the symbol gamma, also called propagation coefficient. It is a measure of the change undergone by the amplitude of the wave as it propagates in a given direction. It is used to determine the reduction in current or voltage with distance as a transverse electromagnetic wave propagates down a transmission line. Now we can solve for this propagation constant mathematically by this formula. Gamma is equal to alpha plus j beta. Or we can solve for it another way. Gamma is equal to the square root of the quantity r plus j omega L times the quantity of g plus j omega C. Now you know the second variables. You've seen this with the solving for a characteristic impedance given the lumped parameters. But what are this alpha and beta? So alpha is the attenuation coefficient. We should convert it to nepers per unit length before using this formula. And beta is the phase shift coefficient, which should be in radians per unit length for this formula to be applicable. Now alpha, the attenuation coefficient, can be solved using this formula. Alpha is equal to R divided by 2 times Z sub O. R is the series resistance in ohm per meter, and Z sub O, of course, the characteristic impedance in ohms. Now for beta, beta can be solved by this formula. Beta is equal to 2 pi divided by lambda. Lambda is a signal wavelength in meters. So I believe you know how to calculate for this lambda. It's just the speed of the transverse electromagnetic wave, which is usually the speed of light, divided by the frequency of the wave. Now we can use another formula for beta. If in free space or homogeneous, we can solve for beta using this equation. Beta is equal to omega divided by c, or the speed of light. And we can also solve for it in terms of permeability and permittivity. Using this formula, beta is equal to omega times the square root of permeability times permittivity. However, In other mediums or non-homogeneous mediums, we have this formula instead. If in terms of velocity of propagation, we have beta is equal to omega divided by v sub b, or the velocity of propagation. V sub b is lower than c, since a transverse electromagnetic wave traveling in a medium other than free space is, of course, slower than its speed in free space. So v sub b is lower than the speed of light in free space. And we can also solve for beta in terms of inductance and capacitance if it is in a non-homogeneous medium. So we're gonna use this formula. Beta is equal to omega times the square root of inductance times capacitance of the transmission line. Now you've seen this unit, Neper, the unit for alpha. Now what is Neper exactly? The Neper is a dimensionless unit used in telecommunications to express the ratio between two measurements of power. Its symbol is NP. The Neper is the natural logarithm of the power ratio. So the formula for Neper given two powers is this. Neper is equal to 1/2 times the natural logarithm of P1 divided by P2, in which case P2 is our reference power. Now we can also convert Neper to decibels and vice versa. 1 Neper is equal to 20 over ln of 10 decibels. So 20 log sub base 10 of E decibel is approximately equal to 8.685,889,638 decibels. That's it for now. Next time we'll take a look at sample problems so that we can apply these formulas in practical applications.